Integrated Math 1. Welcome to lesson 5.2.1. We're starting a whole new unit. We're going to be looking at rigid motions on the coordinate plane and all that good stuff. We're just going to start talking about transformations. Woo. So we're going to really focus in today on geometric components of rigid motions. So you're going to need a few things. You need your workbook. Of course, you can see over here, we're on page M5-53. You know where we are. You're also going to need a compass. That'll be useful. Straight edge, useful. I know we used these last time. We're going to use them again today. And of course, a pencil to help take your notes, write your things, do all the bits. So got all your stuff ready to go? Let's do this. So our learning goals for today's lesson, we're going to make sure that we know precise definitions of a line, segment, angle, and distance along a line. We're going to construct parallel lines. That's the big one. That's the big goal for today. Don't mind the trucks outside my classroom, as always. But that's the big one. We are going to construct parallel lines. That's going to be our big goal for today. So our key terms: point, line, collinear points, line segment, angle, ray, rotation angle. Oh my gosh, we have a whole bunch of key terms today. So you know a lot about rigid motions. And when we're talking about rigid motion, we're talking about things like translations, reflections, rotations. They're not totally new or foreign to you. You've probably seen them before. But now we're going to dig in a little bit more on how do you use straight lines and angles to represent rigid motion transformations. We're going to play with that using our construction tools now that we know how to construct things with these tools. So over on page M5-54, we have our getting started activity. So we have these things called transformation machines. You've learned about function machines, which take a value as input and output another value, right? It's a function. You plug something in, it spits a number out. In this topic, you will learn to think about geometric rigid motions as functions. So these functions can be represented with function machines as well, or in this case, we're going to call them transformation machines. So basically, we're taking a geometric figure, we're plugging it in, and it's going to spit out a geometric figure. And we call those transformation machines. So on the page here, if you look down on page 54 further down, each transformation machine on the left shows a different rigid motion. So for each transformation machine on the right, draw an input shape. And they said to use patty paper. If you have it, that's great. If you don't worry about it. But basically, you're going to draw a shape here for your input. See how the triangle looked like this for the input? And then apply the transformation and draw the output shape. So to give you an idea, we've got a couple of these. We've got 3 of these. So for part A, I input a triangle that looked like this. But the output that it spit out was a triangle that looked like that. Does that make sense? So come up with some other shape. It can be whatever shape you would like it to be. You can literally come up with any shape you like for your input and then draw what it would look like for your output. I don't care what shape you use. Maybe you want to use a different shaped triangle. Maybe you want to use a rectangle. I don't know. What do you want to use? Input some shape. What would the output look like? Given what you see happening here, what would it look like? You're going to do that for all 3 of these, for A, B, and C. So go ahead and hit pause. You can do a different shape for each one if you like. Hit pause, input a shape, show me what the output would look like. So go ahead and hit pause to work that out. Hit play when you're ready to check your work. And of course, it's when I stop talking that the trucks go away and it's finally quiet. So awkward. So anyway, I input the shape and it looks like my shape got turned, right? Like I had the short side of the triangle and the long side, but then the short side was on the bottom and the long side was over here. So it looks like I should turn my rectangle. So I'm going to do that. So now the long side's over here. This is not the best that I've ever done. And the short side is over here. Not the best ever. I have a different shape. Maybe it would help you see it better. If I erase this one, if I did this shape. So I have a circle with a chunk cut out of it, and it looks like I turned it such that the side is now the bottom. This bottom is now the side, right? It looks like I just I just turned it, right? Like I just turned it. Sweet. Swung it around. How'd you do with B? They input the same triangle, and then it looks like they flipped it, right? It looks like they did like a mirror image of this thing. Like they just like flipped it over the line. So whatever shape you want to put in here, you can pick whatever shape you like. What if I do like a slightly different triangle? Like what if I do a triangle like this? It's like a really skinny triangle. And I flip it. So that means I still got the skinny side here, but now my long side is on the right instead of on the left, right? My long leg, and that triangle's better than my first. So erase it. There we go. And again, you may have totally used a different shape, and that's okay. But it looks like I flipped it, right? I just was like, whoa, like a little mirror image there. How'd you do with part C? For part C, I just followed the line, right? I didn't turn it. I didn't flip it. I just shifted it over. I just like scooched it. So like maybe if I did like a rectangle, and again, you could do fancier shapes if you like. If I did a rectangle, I'm just going to like scoot my rectangle down, right? And it's just now going to be like, in fact, I did a bad job of my rectangle. I'm going to show you a better rectangle. So I'm going to make sure my rectangle touches the line, and then my new rectangle touches this side and it touches the top there. So I just scooted it down so it touches the side here and it touches the top right there. So I just like scooted it like over and down. That's all. That's it. Can you identify the rigid motion represented by each transformation machine? Like for A, B, and C, what are the official names of these rigid motions that we just created? Hit pause, write them down, hit play to check your work. I'm going to come back and look at them just because it's easier for me. You guys have them on the page next door. I don't. I'm going to come down. It looks like we rotated this around. So I would say that A is a rotation, right? I rotated it around. For B, it looks like I said flipped it, but maybe that's not the best word. I also mentioned it looked like a mirror image. Reflection. Yeah, we just reflected it from one side to the other. We just flipped it, reflected it. And for this one, I just like shifted it, followed the line, right? I just shifted it following the line. I didn't turn anything. I didn't flip anything. Remember, that's called a translation. Yeah. So A was a rotation. We turned it. B was a reflection. We flipped it. And C was a translation. We just slid it over. Sometimes it's called a slide, but that's a translation. Good stuff. So on page 56, I'm 5-56, let's talk. In the previous lessons, you constructed perpendicular lines using a compass and a straight edge, right? You use these, made perpendicular lines. You can also use these to construct parallel lines. Yes, you can. Oh, wait for it. It's so magical. Just to remind you, there is more than one way of doing this. I'm going to show you 2 different ways that you can do this. I have my favorites. You might have your favorites too. But I just want to remind you of a few little things. Recall that when a pair of parallel lines is crossed by a transversal, so remember matching arrows. See how they have a little matchy arrow? That means that lines M and L are parallel, okay? When you have a line that intersects both of those lines, we call it a transversal. Again, it's been a while since 7th grade. I know. So you have that transversal, which we're going to call line T. Several pairs of congruent angles are formed. So I have 2 parallel lines, I have a transversal, and it creates a whole bunch of angles. And there's a whole bunch of these that are congruent. For example, corresponding angles that are in the same place, right? Like angle 8 and angle 1. See how they're in matching positions? We call them corresponding positions. We call them corresponding angles. They're congruent. They're equal to each other. Angle 8, since these lines are parallel, angle 8 and angle 1 should be congruent to each other, okay? But we have other kinds of angles that are also congruent to each other. I'm going to use another color just to kind of help us see things a little better. Other kinds of angles, like what we call alternate interior angles, which is a mouthful. I get it. But we would say they're on alternate sides of the transversal, so opposite sides of the line, different sides of the transversal. And they're interior, so they're inside of our parallel lines. So I would say like angle 6 and angle 1 would be alternate interior angles, right? Because they're on different sides of the transversal, alternate sides of the transversal, and they're on the interior of my parallel lines. Those guys are also congruent. Those guys are also equal to each other. So just so you know where that came from. And one more. I need one more color. More colors. We also have something, if we have alternate interior angles, you can also have alternate exterior angles. Ooh. Yeah, you can have alternate exterior angles. So again, those are angles that are on alternate sides of the transversal, so different sides of the transversal. And they're on the exterior of my parallel lines. So like, for example, I would say that 4 and 7 are alternate exterior angles because they're on alternate sides of the transversal, right? You see this guy's on the left, this guy's on the right, and they're on the exterior of my parallel line. So I would say alternate exterior angles. Those guys are also congruent. So angle 4 and angle 7 are also congruent to each other. So you get a whole bunch of congruent angles when this happens. This can work to our advantage. Let me show you what I mean. On page 56 here, consider the two segments, segment AE and segment DB, that are shown. The line segments, AE and DB, are parallel. How do you know that? Can you hit pause and just jot down some of your thoughts on how you know that AE is parallel to DB? Hit pause, jot down your thoughts, hit play to keep the discussion going. So you probably worded it differently than I did, but here's what I noticed. These guys are perpendicular. Do you see that? How AE is perpendicular to AD, but DB is also perpendicular to AD, right? They're both perpendicular to the same line. Oh my gosh, these angles are all congruent. Look at those. Look at those angles. All right angles. Psh. Because I have a bunch of congruent angles, it does mean that these lines are parallel. So because AE and DB are perpendicular to the same line, they're parallel to one another, right? AE and DB are both perpendicular. That says DE. That should say DB. Sorry, I'll fix that. DB are both perpendicular to AD. So AE and DB are parallel to one another. Again, those should both have B's on them. Sorry. Here, shall I make them into B's? Again, you probably worded it a little differently than I did. Like my E is about to become a B. Oh, look, now it's a B. Hey. It's good enough. Yeah, so these guys are both perpendicular to the same line. They're parallel to each other. So this may be a bit of a stretch, but I think you can do this. Use your reasoning from question 1 to construct a line parallel to line M through point A. Describe your process, and I'll give you a hint. Start by making a line perpendicular that goes through A. Start there. I know you know this trick. So go ahead and pause. Play with the perpendicular trick a little bit from the last unit to see if you can create some parallel lines. Hit pause, work it out. Hit play when you're ready to check your work. Now, I have, of course, a little answer that's going to pop up on the screen, but we know that's not the most helpful thing. So, say hello to my little friend, also known as my camera, only if my camera chooses to work. My camera is not choosing to work. Hang on. We're going to get it to work. Give me a sec. Or not. Maybe the camera has decided it does not want to play nice anymore. No! That's very sad. When in doubt,